So, how to fold a forest is the name of the talk, and it's about recursion schemes. So, recursion schemes are basically kind of exotic folds, the most basic of which is a catamorphism, and unfolds, which the most basic and common is an anamorphism. And we'll get to that in a bit. But basically, there's this library called Matryoska, which is used for doing generalized recursion schemes. And it's based on Scala Z. And don't be off-put necessarily by Scala Z. We were using cats in the project that we were using it in. And it's easy enough to convert between the two, if you prefer one of them. So folds, what is a fold in the kind of abstract sense? So if you have a structure, some kind of list or tree or something like that, and you have a rule that takes kind of an accumulated value and a part of the structure, so maybe a small segment, and some already folded up thing, then you can take it and turn it into a more collapsed thing, right? A more folded up element. And when you apply the fold to the structure, when you apply this rule over and over again, you end up with just a single value all folded up. And somehow implicit in the rule is what to do when you have no folded up value yet, and that will become apparent later. And so, what is this thing? An unfold, probably a little bit less familiar. So this is when you have just some value, and you have a way of kind of taking that value and expanding it into some structure, and you can kind of apply that then recursively, and you get a resulting structure. So let's say you have an integer, and then you have something that builds up a string and an integer. Then you can apply it over and over again, and you have a list of strings. And we can do something similar on a tree. And this time, our rule would take, say, a node and two children, which are already folded up this time, and map it to a new folded up value. Okay? And then what that'll do is kind of take your tree, start with the leaves, and then repeatedly fold it until you get a single value at the end. And for an unfold on a tree, you take a single value and you kind of do the opposite thing, right? You build a node and you put two children, which you can then repeatedly unfold into an entire tree. Okay, so let's put that to one side for a second, and we're going to talk about fixed point types. Okay, so these are these strange things that are kind of like a option of option of option of option of option forever. Okay, and okay, forget about why you might want to do that. We'll get to that later. But how on earth would you express this thing in Scala? Because you obviously can't write out option forever. So I mean, we're functional programmers, right? So we reach for recursion. So this is a recursive definition of this option of option of option thing, where you just take x and you define it to be equal to option of x. Okay? But there's nothing special about options, so you can do that for any f. And even that is kind of not really satisfactory because, you know, then this f has to be kind of defined outside. So what we can do is define this fix thing, which takes a type constructor f and gives you this same recursive definition. So we have fix of f is equal to f of fix of f. And if you see, it's the same as the line above, but just with fix in place of f, x. Okay, so we say that x is a fixed point of f if x is equal to f of x. And so that means, recursively, that x is f of f of f of f. And fix of f is then a fixed point of f. And you can see that because you have fix of f, which is equal to f of fix of f, an f of f of f of f of f of fix of f. Okay, so now we have our option example that we had before. So fixed option is just fix of option. Okay, this is option of option of option. And these kind of look like this, right? So you have sum of sum of sum of none. Okay, so that's kind of a familiar structure on some level, right? It kind of looks a bit like this. So we kind of have these successive things going on, and eventually we have the end. But there's no other information in this sum other than the fact that there's a next element. So this is kind of like a list of units. Okay, and it's also kind of like natural numbers in some way as well. You have this initial 0 element, and you keep adding successes. Okay, so how about this one? Any ideas? You can shout out.
List of int?
Yes, list of int. Who said that? Yeah, well done. Okay, so that is sum of 1, sum of 2, sum of 3, and 1. So it's kind of, as it says, like a list of int. Okay, how about this one? So now instead of a single successor, you have 2 successors. 3? Yeah. So it's a binary tree. And then this one, where we've replaced the option type with a list. So at each level, you can have as many successors as you want, and we kind of start with a level rather than a root. So this is kind of like a list of trees, or sometimes known as a forest. Okay. And I was a bit sneaky before, and I kind of lied. So this first definition here, you actually can't do that in Scala. You're not allowed to do recursive type definitions like that. But you are allowed to do recursive class definitions. So what you actually have to do, and what Matryoska does, is this second case class thing, which basically is quite annoying because you then have to, instead of just writing sum of sum of sum of none, you have to write fix of sum, fix of sum, fix of sum, fix of none. Okay, which is kind of verbose, and I like to write helper functions to build these things up that kind of take away the fix, so you don't have to worry about it when actually doing this. Okay, but how does this help us with folding? So if you have the usual way of defining this stuff is like with a recursive case class or something like this. So this is the usual way you would do it, which is you have a tree with a value and some children which are also trees. So there's kind of some recursion going on there. And what we've done is taken out this recursive call to the tree in the children and put a type parameter instead. And then put the recursiveness back into it by using this fix. Okay? And what this allows us to do is express this rule. So here we have the 2 children can be of different types. So we can do this kind of thing. So we can define a tree f of int, so the children are ints, to an int. Okay? And then in this case, say we have a tree and we take just the value of each node, so the string, we take the length and then just add on the sum of all of the children, which are already ints. Okay, and that is going to give us, when we do the fold, it's going to give us the total length of all of the values. And in order to do the fold, we call this .kata. And Matryoska gives us that, and that is for catamorphism. Okay, so here we're going to do a full example where this should all compile, which before now it hasn't. Okay, so the first thing we need actually is a functor for our int list. And if you're confused about that, all it means is that you've got a map function on your int list. And don't worry too much, because any algebraic data type will always have a functor definition, and it should be fairly simple to define. So the map function lets Matryoska know where to iterate, where to apply the next step of the rule. And it kind of does this for you, but you have to have the map defined. So let's say we want to have our rule. So in the kind of category theory language, which is where all of this stuff comes from, this is called an algebra. And if you think of normal algebra, you know, you have like two integers added to each other, then you're kind of taking a combination of two things and mapping it to a single thing of the same type, so two integers to one integer. And in this case, we have some structure with integers maybe, and we map it to a single integer. Okay, so let's try and define some kind of toString function on our int list. Okay, so this is a algebra we're defining for our fold, and all we do is, if we have no successors, then we add a few exclamation marks, and otherwise we append the next value, which is already a string, to our value as a string. Okay, and notice how similar this is to foldLeft. We've kind of been forced to define our 0th case, our initial base case, and then the successor step. Okay, so here is an int list. Again, we have to put this fix everywhere. And then we can just import this magic Matryoska thingy and call .kata on the list, and we get the toString value of fold. Okay, so how do we fold a forest? So this is a forest, and this is how we're going to fold it. So again, we're going to do some kind of toString on forest. Okay. Right, this bottom bit will stay on the next slide. So it's up here. So what we're going to do is start by just taking the least part of it. And this is where the forest is kind of empty at the bottom. So below each of these nodes, you actually have an empty forest. Okay, so that's where the recursion starts. Okay, so we get our forest in to the Anamorphism. And then, as I said, this is empty, so we get an empty level here. Okay, map does nothing to an empty list, and then we do make string. So we just get an empty string. Okay? So all of these things below them then end up with empty strings. Okay, next step, we have these forests. Okay? And each of them have their child of a emptied string. Okay? So this list we get in here of this left case is 4 empty string, 5 empty string. Okay, and then we kind of map over them and just take the value to string, because this we get rid of this case here, and then call make string on that. Okay, then we have another level here, and what we do is we just go into the second case when we map and take the value of the node of the tree and the child string. Okay, and then we call make string again. And then we have a final step, which just takes the whole remaining forest and does the same thing. Okay, and that's our kind of toString on the forest. Okay, cool. So anamorphism or unfold. So when we actually used this, what we did, we were using it for a project that had a lot of trees, and basically what happened was we did some NLP parsing on some text, and then we got this thing called a dependency tree. And this is like lots of different segments of text arranged in a tree with the relations between the text, how the different components of the sentence or whatever kind of relate to each other. But this was a Java library, and we had some horrible mutable stuff going on. And basically we wanted to lift it kind of into this fixed kind of structure so that we can do our fancy folds and unfolds and things on it. So how do we do that? So we can just apply an unfold to the dependency tree. So we have a rule, which is called a co-algebra when you're unfolding. It's the dual of an algebra, where you flip the arrows basically. So you have a dependency tree to an NLP info of dependency tree here. And basically, what we do is we just take the dependency tree, put the values we care about in, and we just put the child relations, which are also dependency trees, straight in there. And then Matryoska does all the stuff for us. And then we can just call this .ana, which is anamorphism on the dependency tree. And what happens is, start with a dependency tree, map it to an NLP info, and then the childs are the dependency trees. And we just keep doing that until we build up our fixed point tree. Okay, so this is sort of a comparison of the anamorphism way of doing it on the left and the way you would do it with a recursive function on the right. So there's not much in it really. I mean, this map function we have to do here is the recursive call. But there's not much difference really, there's not much benefit. But let's say now the child relations are going to be a future of list of dependency trees. So you've got to call some database together. What we can do with Matryoska is just add this m here, so call it ana m, future. And then we can just take our future child relations and map it and build up the same structure. So there's not much difference here conceptually of what's going on. But what we would have to do if we're doing a recursive function is we'd have to call this flat map and then traverse over the recursive call and then map it into building up the structure. And you can imagine as more stuff and more complexity starts happening, you get more of this stuff kind of getting in the way and taking away from your logic in your mind of how this thing's working. Okay, and I said before that we needed a functor definition, but if you're doing this sort of thing, you need a traverse definition for your NLP info F here. Okay, so when would you use it? Well, when I would use it is if you have a project that has many recursive functions called on a recursive structure, and you have to be careful because you don't want to just fill with all this crazy complicated category theory stuff. So I would say don't do it on lists because you already have foldLeft. You already have, cats gives you foldLeft m. It's not necessary. But if you have trees and things like that, it is actually quite helpful sometimes. And if, as I said, the folds are actually quite complex, then it can be useful to kind of clear up some of that syntax sometimes. Okay, and if you do use this, kind of use helper functions to get rid of those fixes that you have to write everywhere. Help out inference. Sometimes the compiler starts hating on you because you can't work out what's going on. So just put in the type signatures, put in the type parameters, and that should help. And kind projector, if you know what that is, it's a compiler plugin. It's also very helpful when doing this stuff. And I have to show this thing. So this is on the Matryoska GitHub page. And it shows you all of the kind of crazy stuff you can do. I mean, we just scratched the surface of this catamorphism and anamorphism at the top, but there's like so much crazy stuff you can do with it. And finally, don't be scared. I mean, I know this thing is intimidating, but it is actually quite good once you get your head around it.